Big Bang. This type of radical revolution in the scientific worldview has not occurred, perhaps considering the recognition of the heliocentric machine. But then, two similarly hard questions arose. First, what certainly became before the Big Bang? What turned into space like before it started to amplify, and how lengthy did it stay in this primordial kingdom? Secondly, everything that has a beginning has an end. So what can be the end of our universe? The English physicist Brian Cox got down to locate an answer to this question. Now, in a world-shattering revelation, physicist and professor of particle physics Brian Cox has just declared that he strongly suspected that the universe existed before the Big Bang, throwing the theory of our origins on its head. We used to assume that the universe emerged in that state, very hot and very dense, at the beginning of time, and we used to call that the Big Bang. But now we strongly suspect that the universe existed before that, and in that sense, it's possible to talk of a time before the Big Bang. Join us as we dig deep into how Brian Cox just debunked the Big Bang. Professor Brian Cox has transformed his field of science in the 21st century into something accessible to anybody, often contributing to public debate and discussion. Never one to pull away from the big questions, the physicist previously took on the tail of the Big Bang. The concept of the Big Bang first came about in the 1920s and 1930s when we looked out at remote galaxies. We discovered something unusual. The farther from us they were, the quicker they seemed to be receding from us, consistent with the predictions of Einstein's general relativity. A static universe would be gravitationally risky. Everything needed to either be moving away from each other or collapsing towards one another. If the fabric of space abides by his laws, the observation of this apparent recession taught us that the universe was expanding. Today, if things are getting farther apart as time goes on, it means they were nearer together in the distant past. An expanding universe doesn't just mean that things get farther apart as time goes on. It also means that the light present within the universe stretches in wavelength as we travel ahead in time. Time, since wavelength determines energy, and meaning the universe cools as we age, and thus things were warmer in the past. Extrapolate this back far enough, and you will come to a time where everything was so warm that not even neutral atoms could form. If this photo had been accurate, we should see a leftover glow of radiation today in all directions that had cooled to just a few degrees above absolute zero. The discovery of this cosmic microwave background in 1964 by Arno Penzias and Bob Wilson was a breathtaking confirmation of the Big Bang. It's tempting, therefore, to keep extrapolating backwards in time to when the universe was even warmer, denser, and more compact. If you continue to go back, you will find a time where it was too hot to form atomic nuclei, where the radiation was so hot that any bound protons and neutrons could be blasted apart, a time where matter and antimatter pairs could spontaneously form as the universe was so energetic that pairs of particles and antiparticles could spontaneously be created, a time where individual protons and neutrons break down into quark-gluon plasma. This sets up a very special photograph of the beginning of what brought about a Big Bang. Instead of the emergence of time and space from a singular state, now we get to deal with the really big questions. What does all of this mean for the right beginning of the universe if one of these things even existed? Well, the bottom line is probably the recent Big Bang really happened, but it doesn't increase to go all the way back to an arbitrarily hot and dense state. Instead, the very early universe underwent a period of time where all the energy that could move into the matter and radiation present today was instead sure up within the material of space itself. That period, called cosmic inflation, came to an end and gave rise to the new Big Bang, but never created an arbitrarily hot dense state, nor did it create a singularity. What happened prior to inflation, or whether inflation was everlasting to the past, is still an open question. But one thing is for certain: the Big Bang is not the beginning of the universe. But if the Big Bang wasn't the beginning, what was it? What happened before the Big Bang? Short answer: we don't know. Long answer: it might have been a lot of things, each mind-bending in its own way. It's possible that before the Big Bang, the universe was an endless stretch of an ultra-hot, dense material persisting in a constant state until for some reason the Big Bang occurred. This extra-dense universe may have been governed by quantum mechanics, the physics of the extremely small scale. The Big Bang then might have provided the moment that classical physics took over as the primary driver of the universe's evolution. For Stephen Hawking, this moment was all that mattered before the Big Bang. He said events are unmeasurable and therefore undefined. Hawking called this the no-boundary concept, in which time and space are finite but have no boundaries or beginning or ending points. The same way that the planet Earth is finite but has no edge. Or maybe there was something else before the Big Bang. It's worth pondering a bold idea Professor Brian Cox suggested. There was a time before the Big Bang. A time where the universe did not exist at all. He explored this in his documentary series, Universe, stating that before the launch point of the Big Bang, there was no matter at all. All that existed was space-time and an ocean of energy, almost still but gently rippling. This space, as he said, should be imagined as a near ocean of energy filling the void. It could have had no structures, and the energy in the space could have caused it to stretch violently. Something appeared in space as inflation. Flipping the Bible creation story on its head, Brian Cox proceeded to explain the scientific creation story. The crux of the story is an unimaginably violent expansion known as inflation, he said. In the beginning, there was an ocean of energy that drove a rapid expansion of space called inflation. There were ripples in the ocean. As inflation ended, the sea of energy was transformed into matter through the Big Bang, and the pattern of the ripples was imprinted into our universe as regions of slightly different density in the hydrogen and helium gas that formed shortly after the Big Bang. The denser regions of gas collapsed to form the first stars and the first galaxies, and 9 billion years later, a new star formed in the Milky Way, the Sun. The star was joined by 8 planets, including Earth, and almost 13.8 billion years after it all started, we emerged blinking into the light. Brian Cox isn't the only one to make such an argument about the beginning of the universe. Great theoretical physics research has discovered a possible window into the very early universe, showing that it may be just the latest cycle of a bang-bound cycle that has been going on well at least once and probably all the time. According to the study, the physics we need to understand the early universe is a perfectly complex mishmash of general relativity and high-energy particle physics, and can only take us so far before breaking down as we try to push deeper into the first moments of our cosmos. The math gets harder and harder to solve, all the way to the point where it just quits. The main sign that we've got terrain yet to be explored is the presence of a singularity or a point of infinite density at the beginning of the Big Bang. Taken at face value, this tells us that at one point, the universe was filled into an infinitely tiny, infinitely dense point. That is obviously absurd, and what it really tells us is that we need new physics to solve this problem. A model of physics that is capable of handling gravity and the other forces combined at ultra-high energies, which means that string theory claims it can explain the earliest moment of the universe. One of the earliest string theory notions is the erotic universe, which comes from the Greek word for configuration or hearth. In this scenario, what we know as the Big Bang was sparked by something else going on before it. The Big Bang was not a beginning but one part of a larger process. Extending the erotic idea has led to a theory, again encouraged by string theory, called cyclic cosmology. Technically, the idea of the universe constantly repeating itself is hundreds of years old and predates physics, but string theory gave the idea firm mathematical grounding. The cyclic universe goes about exactly as you might imagine, constantly bouncing between big bangs and big crunches, probably for eternity back in time and for eternity into the future. As cool as this sounds, early versions of the cyclic model had difficulty matching observations, which is a big deal when you're trying to do science and not just telling stories around the campfire. The main hurdle was agreeing with our observations of the cosmic microwave background, the fossil light left over from when the universe was only 380,000 years old. While we can't see directly past that wall of light, if you start theoretically tinkering with the physics of the infant cosmos, you affect that afterglow light pattern. So, it seemed that a cyclic universe was a neat but wrong idea. But the erotic torch has been kept lit over time, and in recent years, many physicists have explored the wrinkles in the mathematics and exposed some previously ignored possibilities. These scientists, studying the idea of the Big Leap, suggest the universe is expanding and contracting, swinging back and forth in a vastly larger picture timeline. Some bouncers believe this happened just once, while others believe cyclic bouncing is what makes our universe. And while the Big Leap still requires big leaps that must be explained with generous scientific hand-waving, proponents say it's a lot less so than with a model of the Big Bang they say is fatally wrong. The Big Bang, as suggested, is based on an idea called inflation. The field of cosmology, especially regarding the rapid expansion after the Big Bang, includes some grand and imaginative concepts. Critics of inflation theory argue it's overly neat, probably contrived. But inflation suggests an infinite number of universes, with our observable universe being one isolated bubble among many. This challenges the idea of a unique beginning and prompts questions about what may lie beyond our own bubble. Alternatively, proponents of the Big Leap theory propose a cyclical universe, potentially offering a more complete explanation without the need for a multiverse. This theory proposes that before the Big Bang, there existed another universe with entropy increasing toward the past, suggesting time could run reverse to our universe. This anti-universe concept could explain dark matter as a form of ghostly particle called a neutrino specific to its own universe. Moreover, extending the CPT symmetry to the entire universe implies the existence of a mirror image cosmos where every aspect of our universe changes parity and time is reversed. These ideas challenge traditional views of cosmology and suggest there is still much to explore and understand about the nature of our universe. The idea of a CPT mirror universe suggests it exists beyond our Big Bang, potentially before the start of our observable cosmos. Researchers suggest various observable outcomes. Neutrinos should exhibit Majorana behavior, meaning they are their own antiparticles. One neutrino species should be massless, a large, testable prediction in this model. Inflation never occurred because the universe was simply packed with particles. The absence of primordial gravitational waves, if confirmed by experiments, could support this model. Understanding the origin of the universe pushes the boundaries of our knowledge. We cannot understand the initial state of the universe with certainty, which prevents us from achieving a complete theory of everything. Scientific progress has revealed a detailed cosmic history, but gaps remain, including the nature of dark matter and dark energy. The question of the first cause remains open, prompting humility in the face of the unknown. Scientific inquiry, unlike supernatural reasons, is based on evidence and facts as opposed to faith. When considering the origin of the universe, especially the concept of what existed before the Big Bang and the causality of the Big Bang itself, current cosmology provides a complex and evolving picture. The traditional understanding, inspired by religious and philosophical beliefs, initially posited a divine creation or an eternal, unchanging universe. This changed in the early 20th century with the arrival of observational evidence suggesting the universe is expanding. The discovery that remote galaxies appear to be receding from us led to the idea of cosmic expansion and eventually to the formulation of the Big Bang theory in the 1920s and 1930s. The idea gained further support with the discovery of the cosmic microwave background radiation in the 1960s, a remnant of the hot, dense state of the early universe. But the Big Bang theory itself raises profound questions. What existed before this event? If anything, was there a time before time, and what would that mean? These questions challenge our understanding of both cosmology and physics. The idea of before the Big Bang is particularly elusive because the Big Bang marks the beginning of both space and time as we know them. One interesting thought comes from theories such as cosmic inflation and string theory. Cosmic inflation suggests that the universe underwent a rapid expansion phase in its earliest moments, driven by a field called the inflaton. This inflationary period explains the uniformity and flatness of the universe observed today. String theory, on the other hand, attempts to unify all fundamental forces of nature, including gravity, and proposes that the universe's origin may be more complex than previously imagined. Furthermore, recent developments in theoretical physics and cosmology have suggested alternative scenarios to the Big Bang. For example, cyclic models suggest that our universe goes through repeated cycles of expansion and contraction, with each cycle beginning anew after a big crunch phase. These ideas challenge the notion of a singular beginning and open the possibility that our universe is just one phase in a larger, eternal cycle of cosmic evolution. The search for answers continues with ongoing advancements in observational astronomy, particle physics experiments, and theoretical modeling. Each new discovery adds layers to our understanding while posing new questions about the ultimate origins and fate of the universe. As scientists delve deeper into these mysteries, the quest for a comprehensive theory of everything integrating quantum mechanics and general relativity remains a major goal, promising insights into both the microcosm of particles and the vast expanse of the cosmos.